Okay, it's recording now. So this is group three for the MA 94 project presentation. I'm Connor.
I'm Yena.
I'm Ryan.
I'm Jeffrey.
All right, cool. So first slide, we have the introduction.
So for the introduction, with this final project, we aim to create a robotic manipulator utilizing tools and skills we learned throughout the course, including visualizing mechanical components using SolidWorks, which is a computer-aided design software. And this project presents a comprehensive exploration of a research, design, and manufacturing of our robotic arm gliding gripper gadget, which highlights its functionality and potential to complete tasks.
And for the prior work, robotic manipulators have been used in various industries ranging from manufacturing to healthcare, increasing human capabilities by automating tasks. Depending on the purpose of the robotic arms, each has differences in their design and functionality. Some examples of tasks that robotic arms can perform include welding and material handling.
In terms of the scientific history, ever since the Unimate introduced the first industrial robotic arm in 1961, a lot of other robotics arms started appearing in first the manufacturing industry, and so these were industrial robots initially designed for assembly lines. Come the modern day, these robotic arms have evolved in strength and dexterity, capability of serving a wide range of uses, from medical prosthesis or surgery devices to construction. And so this is our first concept sketch. This is mine. And so the main point of my design was I wanted to maximize the degree of freedom by having linear bearings at the base, just so we can get X and Y degrees of freedom.
All right, so next is my design, and my design has an idea that the robotic manipulator has 3 rotational degrees of freedom, one of which is 360 degrees as shown by the project guidelines.
And here we have my concept. And my concept mainly focuses around the claw because I was really interested in how the claw works. And as for the degrees of freedom, they only have the 3 rotational.
So this is my concept idea, and I focused on the rotational part of the robotic arm and how the claw mates to the arm and the way it allows the rotation.
So our final agreed upon sketch ended up with 5 sub-assemblies, that being the base, the linear bearing at the bottom, the lower arm, upper arm, and the claws. The whole idea is that we would have 3 degrees of rotational freedom, as well as the X and Y directions. It was based off the 3D printer base, the way that those tend to move in the X and Y directions.
All right, next is the design specifications. The design of the device is that of a standard robotic arm with 3 rotational degrees of freedom, with a linear bearing base design that allows translational movement in 2 axes, functionally similar to a 3D printer base. It has a total of 28 unique components, 5 sub-assemblies, and is powered by 6 electric servo motors. The overall dimensions of the fully assembled gliding gripper gadget are 371 millimeters in length, 326 millimeters in height, 371 millimeters in width, and 2.69 kilos in weight.
So first we have, I guess, my sub-assemblies. And so the whole base of the robotic arm was split into 2 smaller sub-assemblies, that being the base that serves as a rotation, and then the 2 linear bearings that serve for the X and Y degrees of freedom. And so here we have the base that connects directly to the lower arm, and this is the one that grants rotational freedom. And so this is composed of 5 unique components. From the top down, we have the motor cover, which alleviates some of the weight from the motor itself and imparts it on the mounts. We have the motor bracket that connects the motors to the 2 lower brackets below. Those connect to aluminum rods, and then we have a final horizontal base bracket. And these are all held together by M5 head socket screws and nuts, while the motor itself is attached to the motor bracket via M2.5 screws. Next, we have the linear bearing. Again, this was based off the 3D printer bed design, and it achieves X and Y directional movement with the control of motors. So this one has six unique components, that being the motor holders. Those are going to be the L-shaped things on top of the motor in the assembly. We also have the load support, which are on the opposite side of the motor. That just keeps the aluminum rods at a set level. We have wheels that are attached to the motors, and these go along the the base of the linear bearing, and that's how the motor ends up uh, granting X and Y degrees of freedom.
So here's a lower arm which is connected to the base and enables the rotation of the arm 360 degrees and in the yaw axis, and it uses a motor attached to achieve the forward and backward movements of the lower arm. So the lower arm is considered with the 5 different components. The first one is the base link, which connects the arm to the base, and then the wheel, and then the arm itself, and then the back joint, which connects the whole thing together, and then the arm link, which connects the lower arm to the upper arm.
Next is the upper arm, which is connected to the lower arm and the claw. It can rotate in the pitch axis for 180 degrees and can rotate in the roll axis a full 360 degrees. The attached servo motor powers the upper arm. For the components in the upper arm, there is the lower arm link, the washer and the second washer, all of which are part of the mechanism that connects the upper arm with the lower arm. It fits into the upper arm link that was on the lower arm. And there's the arm itself and the claw link, which allows for roll rotation, roll axis.
And next up, we have the claw. It is powered by electric servo, and the smallest gear drives the neighboring gears to turn, which then turns the claw arms. The claw is able to grip items utilizing the torque applied by the motor. The unique components are 3 gears that are different from each other to match, a pin, a base plate, a flange to attach to the upper arm, a claw gripper arm, and bearings. And besides the pins, M3 and M2 screws are needed to connect the claw to the arm and motor.
And here we just have the final assembly. Um, yeah.
Next is powering the device, and the device is powered by 6 servo motors located in the base, of which there are 3. The motors in the base allow for X and Y axis translation and allows for yaw rotation. And there's one motor in the upper arm which allows for roll and pitch, and the lower arm allows for pitch, and the claw just simply powers the claw.
And here's the working motion animation with the 5 degrees of motion. Here's the X-axis, Y-axis, a yaw rotation, pitch, and roll.
So manufacturing tolerancing, all the parts were designed to be manufactured by means of a standard 3D printer. SolidWorks only had the ABS plastic version, but a lot of PLA plastics are common for 3D printers itself, with the exception of aluminum rods at the base, which can easily be machined in a machine shop or 3D printed as well, without sacrificing too much structural integrity. All screws and holes should have clearance fits. Locational clearance fits are used for the arm parts that are supposed to, rotational clearance fits are used for the parts in the arms that are supposed to rotate. Locational ones are used in translation movements, such as in the linear bearing. And interference fits are used for the parts that are to mate with each other.
So in conclusion, we were able to construct a working robotic manipulator with 5 degrees of freedom using 5 different sub-assemblies and 31 components. Both the base and the arm itself were powered with electric servo motors, and it is capable of tasks such as sorting, handling, and automatize it, picked and placed. In the future, robotic manipulators such as this will most likely implement in new technologies and the fields related to it.